Hi everyone, I'm Pierluigi Zama Ramirez and I will present our paper Open Challenges in Deep Stereo, the Booster Dataset. Me and my co-authors are from the CV lab of the University of Bologna. Stereo matching is a famous computer vision task in which we look for correspondence between two images acquired from different viewpoints. Recently, thanks to deep learning, stereo algorithms reach a high level of accuracy. However, can we really consider stereo matching solved? Our paper is based on the following motivation. First of all, despite error in famous stereo datasets such as KIT has become relatively small, when increasing the resolution they are still high. Moreover, high resolution datasets with precise ground truth provide only few limited samples, thus limiting the research in this field. Another important open challenge regards non-Lambertian surfaces where the matching problem is ill-posed. Estimating the depth for surfaces such as transparent glasses, water, or mirrors is crucial for several applications such as obstacle avoidance and grasping. Moreover, it is becoming more and more frequent in nowadays devices to have several cameras which yet feature different specifications such as field of view and resolution. However, this challenging unbalanced stereo scenario is addressed only by few working literature. Thus, we propose Booster, a novel dataset of both balanced resolution as well as unbalanced stereo pairs, framing a large collection of non-Lambertian objects. To capture high-resolution depth ground truth, we propose a novel semi-automatic data annotation protocol based on a deep space-time stereo framework. We also provide manually annotated segmentation map that identify and rank the hard-to-match materials based on specularity and transparency, which can be useful to analyze the behavior of state-of-the-art networks on these challenging surfaces. We relate on our dataset several state-of-the-art networks, and we provide a benchmark online to gather future works that will address our challenging scenarios. We gather Booster using a custom rig consisting of 3 different cameras. The left and right cameras feature similar specification and form a standard balanced stereo system with images at 12.4 megapixels. Left and center cameras have different characteristics and form an unbalanced stereo system with the center device featuring a wider field of view and a lower resolution of 2.3 megapixels. The dataset acquisition protocol is composed of 2 main steps: calibration and acquisition. During calibration, we first acquire several images framing a known pattern. Then, we follow standard procedures to calibrate both the balanced and unbalanced stereo systems. For the balanced setup, we follow standard rectification. For the unbalanced setup, we follow an unbalanced rectification procedure, obtaining 2 images that are rectified if resized at the same resolution. After the calibration, we are ready to acquire the ground truth of our dataset. First of all, we collect passive images for both the balanced and unbalanced setups at various light conditions. Then, we paint non-Lambertian surfaces and we project a textured pattern onto the scene. We capture several frames which feature different textures for the same static scene. After acquisition, we propose a novel space-time stereo approach. Thanks to the heavily textured scene, it can generate accurate disparity maps using as input both passive and textured stereo frames. However, the depth maps still suffer from typical bleeding artifact of deep stereo networks, and it is estimated at only half of the final resolution. Thus, we propose a novel super resolution and sharpening procedure based on continuous neural representation to upsample and sharpen the depth maps. Finally, we filter out wrong points by using standard filtering techniques and a manual correction process. From the right, we can see that our approach yields very accurate depth maps. From the left, we can see that state-of-the-art stereo networks estimate wrong depth for challenging non-Lambertian surfaces. Together with that ground truth, we also provide material segmentation masks that identify and rank the hard-to-match materials based on specularity and transparency. Finally, to obtain ground truth also for the unbalanced setup, we work depth semantic accordingly to the rectification transformations. Our dataset is composed of 64 labeled scenes for a total of 419 balanced and unbalanced stereo pairs. Moreover, to encourage the development of weakly supervised solutions, we also provide approximately 15,000 unlabeled stereo pairs. We evaluated several traditional and state-of-the-art stereo methods on our dataset. We can notice how all of them achieve high errors, especially when testing at higher resolution. We performed a class-wise evaluation using a pre-trained state-of-the-art stereo network. The network performances decrease when evaluating on surfaces with a higher level of reflectiveness or transparency. After fine-tuning on our training set, the errors slightly decrease. Qualitatively, networks fail, especially on non-Lambertian objects. In the rightmost column, we can see that after fine-tuning on the booster training split, the network has learned to handle transparent objects much better. To conclude, we believe that Booster holds the potential to boost future research in deep stereo. So come visiting our project page and submit your solution. Thanks for your attention.